Okay, so this is going to be like a little prelude to the undetermined coefficients method. And so what I first want to do is kind of outlay the whole theme of the technique, and then we'll do a simpler equation before moving on to the more complicated ones. So here, to just kind of show you what we're up to, we're looking at different non-homogeneous equations, and all these techniques that we're going to look at involve guessing a solution with a certain form and then going in and finding the missing coefficients. Okay, so I'm going to do an example here to highlight the things we have to consider when we do it like this. So if I have an equation, we're going to solve, find a particular solution. All right, and it's y double prime minus 3y prime plus 2y equals 5e to the 4x. So what we'd want to do is here try y particular as being some scalar times ae to the 4x. Okay, and the reason for that is we're hoping that it would end up that if we do double differentiation and multiplication and add it all up, that we would have started and ended with a function like this. Okay, so and then we just need to figure out what a must be. So if we go through and do that, what will we get? Well, we'll get yp prime is 4ae to the 4x. Yp double prime is 16ae to the 4x. And so we'll get, when we substitute into this equation, 16a e to the 4x minus 3 times y prime, which is 4a e to the 4x, plus 2 times y a e to the 4x equals 5 e to the 4x. And then we can just figure out what this a must be by canceling out the e to the 4x, because that can never be 0. And we just get 16a minus 12a plus 2a. This must equal 5. So 16 minus 12 is 4 plus 2. We get 6a equals 5. So a must be 5 over 6. Okay, so therefore our y particular is 5/6 e to the 4x. So this solves our given non-homogeneous equation, meaning it has this forcing function over here. And if we wanted to find the general solution, remember from last time that it's going to be of this form, yc plus yp, so we go in and find the solution to the complementary homogeneous equation for that. Okay, but we won't do that right here. What I want to do is go back to this initial example and say, hey, what if this was switched up a little bit? And that we had y double prime minus 3y prime plus 2y equals 5e to the 2t, or 2x. Okay. So then here what we see, this is a solution to the homogeneous equation. Right, because the homogeneous equation has the characteristic polynomial r squared minus 3r plus 2. So that tells us that r1 would be 2 and r2 would be 1. Right? So, e to the 2x and e to the x are solutions to the homogeneous equation, which I'll write out here just for good note taking. So since this is a solution, it's going to make the left-hand side 0 if I plug it in. So if I guessed that I just had, if my yp was some u times e to the 2x, well, this is going to cause the y term to actually drop out. So what we do instead, or we said not u, but a times e to the 2x. So what we do instead is we'd guess the following, which is guess a times x, so that when we take the derivative, we still have something left over, so to speak. So what we do here, guess this, and then see, all right, well then yp prime is going to be what? So we're going to have a little product rule here, so we'll get a e to the 2x plus 2ax e to the x, 2x. And y double prime gives us, again, 2a e to the 2x plus here, what, 2a e to the 2x plus 4ax e to the 2x. Right. So then we're left with just 4a e to the 2x plus 4ax e to the 2x, which if we pull out the e to the 2x, we're left with 4a plus 4ax. Or you can write it like this maybe. All right, so now when we go back and substitute in, we'll get y double prime, so that's e to the 2x, 1 plus x times 4a, minus 3 times y prime, which was a, we'll do like this. Pull out the e to the 2x, and then we're just left with a plus 2ax, and then plus 2y, and 2y is 2ax e to the 2x. This all equals 5e to the 2x. So obviously e to the 2x's cancel everywhere. We're left with 4a plus 4ax minus 3a minus 6ax plus 2ax equals 5. And then run all this through. So 5a minus 3a gives us a. 4 minus 6 plus 2 gives us 0x, which tells us that a must equal 5. Okay, so this tells us that our solution then, y sub p, is actually 5x e to the 2x, and this will give us our particular solution to this equation. If it were just some scalar, we wouldn't actually end up with anything. So we have to guess this kind of adding in this factor of x in order to not have it drop out. And that's because, again, this guy solved the homogeneous equation, so we had to do this. We had to change this to x. So one last part here, as if we had a repeated root in the complementary equation matching our function, then we'd have to try the next level up. So, for example, if we had something like this, minus 4y prime plus 4y equaled e to the 2x. Let's just do it like this, 4e to the 2x. Well, we see that for the complementary solution, we look at the complementary equation, our polynomial is r minus 2 squared, and if we set that equal to 0, we get r equals 2, which tells us that e to the 2x is a solution, and it's a repeated root with r. So e to the x is a solution, x e to the 2x is a solution. So again, it means that if we use this in our equation on the left-hand side, like we did here, it's going to drop out terms because it's equal to 0 when we plug it in for y. So this tells us then we need to guess yp is a, not times x e to the 2x, but x squared e to the 2x. So again, when we differentiate it twice, we've still got a function hanging out. It's a very loose way to put that. So yp prime and yp double prime. I'm going to let you go through this and work it out using the method we just did. But essentially, you're still going to end up with an equation where you can find a is some number. And then this y particular will solve your equation. And obviously, you can use that to find a general solution. But this is the theme we're setting up. And this added issue of if the right-hand side actually solves the complementary equation, what we have to do to kind of keep it in this form. So we guess the form, and then we figure out what the coefficients must be to make it work out that way. All right. So this is kind of a prelude to the next section where we tack on a factor of not just an exponential function, but then an exponential times a polynomial, and then we'll move into an exponential times a sinusoidal input. And again, so this is all situations where your forcing function, this external force, is non-zero on a system like a spring mass dashpot. Okay, cool.